So now we're going to try to find a relationship between the voltage or the potential of a reaction or a cell and the Gibbs free energy change, okay, or the energy change of a reaction. Now, when we talk about voltage, right, voltage can be defined as the work done per unit charge. So voltage can be defined as the work done per unit charge, right? And we have a relationship that you guys should be familiar with, which is F is equal to LE. Okay, now what is this relationship? Here, capital F stands for Faraday's constant. Okay, this is Faraday's constant. So Faraday's constant refers to the charge on 1 mole of electrons. Okay, Faraday's constant is the charge on 1 mole of electron. Okay, charge on 1 mole of electrons. L refers to Avogadro's constant. Okay, L refers to Avogadro's constant. Right, that is 6.022 into 10 to the power of 23, right, particles per mole. So Avogadro's constant. And then E refers to the charge on an electron. Okay, E refers to the charge on 1 electron. Okay, so the E again is the charge on 1 electron, right? That is 1 eV, 1 electron volt, right? 1.6022 into 10 to the power of negative 19 coulombs. Right, so we want to find the charge on 1 mole of electrons. We know we have this many electrons in 1 mole, 6.022 into 10 to the power of 23, right? I'm using this to more significant figures than we usually do to determine Faraday's constant, right? So we have this many electrons in 1 mole of electrons, and then the charge on a single electron is 1.6022 into 10 to the power of negative 19 coulombs, right? And this gives us Faraday's constant. And Faraday's constant to 3 significant figures comes out to 96,500 coulombs. Okay, so this is the value of Faraday's constant to 3 significant figures. This is the value we will be using in our course. More specifically, Faraday's constant is expressed as 96,500 coulombs per mole. Okay, that is per mole of electrons. Obviously, per mole is not a true unit, right? But it's expressed this way. Okay. The next relationship that we have is that if in a reaction I had n moles of electrons being exchanged in a redox reaction, if I had n moles of electrons, right, the charge is equal to the number of moles of electrons times Faraday's constant, right? Again, obviously, we know that if 1 mole of electrons has this much charge, if I had 2 moles of electrons, then the charge would be 2 times this. If I had half a mole, it would be 0.5 times this, and so on, right? So here again, this is charge, right, in coulombs, and n is obviously the number of moles of electrons, right? N is the number of moles of electrons, and F is again Faraday's constant. So far we've seen the formula Q, F is equal to LE, right? And we've seen the formula Q is equal to NF. And now we're going to derive a third formula. Let's go back to the relationship that we have for voltage, right? We know that voltage is work done per unit charge. That is the work done divided by charge. So when we talk about a reaction, right, W over here, W stands for, the W is basically work done by the cell. Okay, it's the work done by the cell or by the reaction. Okay, by the cell or by the reaction, right? Now, so if you think about a voltaic cell, for example, right, or a voltaic cell, in a voltaic cell we have a reaction taking place that releases energy, right? We're generating electricity that can be used to do work, right? So for a voltaic cell, the work done by the cell is positive, right? If a cell is doing work, it means that the cell is releasing energy, right? So when the work done by the cell is positive, it means that the energy change for that cell is negative. Okay, and the energy change is represented by the Gibbs free energy change, right? So if the Gibbs free energy change is negative, in other words, if the reaction or the cell is releasing energy, then the work done will be positive. Similarly, if the Gibbs free energy change is positive, right, if the work has to be done on the cell, right, then the Gibbs free energy change would be positive, and the work done, instead of work being done by the cell, work would have to be done on the cell, right? That would be an electrolytic cell, right? So we can say that W is equal to negative delta G, right? And we're going to look at standard conditions. So we can say W is equal to the standard, negative standard Gibbs free energy change. Similarly, we know that the voltage for a reaction or for a cell is simply the EMF of the cell or the EMF of the reaction. So we have E naught, right, for V, right? Again, V is again just the E naught, right? The EMF of the cell or the EMF of the reaction, right? And that is equal to the work done, that is equal to the work done per unit charge. The work done is simply the negative standard Gibbs free energy change divided by the charge, which is number of moles of electrons times Faraday's constant. Okay, and from this equation we can derive, or from this we can derive the following expression. That is, the standard Gibbs free energy change is equal to negative N times F times the E naught of the cell, okay, or the reaction. So again, I'll explain this again. If a cell is releasing energy, for example, let's say that a cell was releasing 20 kilojoules of energy, right? Now, if it's releasing energy, we know that the Gibbs free energy change for that cell would be negative 20 kilojoules, right? The system is releasing energy. So that would be negative 20, and therefore the cell would be able to do 20 kilojoules of work. So the work done would be positive. So if the delta G is negative, the work done is positive. If delta G is positive, the work done is negative. So now we're going to be using this relationship. We're going to be using this relationship moving forward, okay? Now the derivation will probably not be tested. However, you should be familiar with this equation, okay, with this expression. All right. What this means is that when the standard cell potential or the standard reaction potential is greater than 0, right, the delta G would be less than 0. The reaction is feasible. Right. If the E naught value, the standard cell or the standard reaction potential is less than 0, then delta G is greater than 0, and we say that the reaction is not feasible. Again, in this expression, N refers to the number of moles of electrons, right? And N refers to the number of moles of electrons, F refers to Faraday's constant, and this refers to the standard cell or the standard reaction potential.